So we're moving into chapter 5, probability, which is sort of the bridge that is going to bring us to ultimately to statistical inference. We understand now how to collect data, surveys and observational studies and experiments. We know how, for sure, know how to get it organized in many different ways. If it's categorical, we have a two-way table, or if we can make a scatter plot and use linear regression, or if we just want to look at one variable statistics and maybe a box plot. So probability really helps us understand what we mean by random chance or something that's statistically significant, right? Suppose we run an experiment, we get the results, and we want to see, are those results statistically significant? We have to lean on the understanding of probability and random chance to do that. It's my favorite topic to study and to teach. I love probability. So one of the things I like to do is this birthday problem exploration. It's a very, very famous problem. In fact, one of my students a couple years ago handed me a Snapple bottle cap, and it was a trivia question under the bottle cap. So we'll try to articulate this so you understand, and then if you have a copy of this, or you can just make a mental note of your number for this. But the initial question goes like this: how many people do we need to have together in a room so that there's a better than 50% chance that two people have the same birthday, just day and month? So if your birthday is the same as mine, my birthday is April 7th. So if you can remember that and, send me something special. I like the Wawa gift cards, especially if you, that'd be much appreciated. So, so maybe somebody in the class shares the same birthday as me, even though not the same year. So that's all we're talking about, same day and month, okay? So I'll tell you, the first time I heard this, I was probably in college, or maybe one of my high school math teachers floated it out to me. I don't know, but I remember guessing something like over 100, like 180. I was thinking, I don't know if I was just, dividing 360 by 2, but that was, somewhat probably around the guess that I made the first time I heard this, better than 50% chance that two people have the same birthday. So one of the ways we can look at this, it's a little bit more advanced of a problem than really you would even need to be able to do in this chapter. We do some more sophisticated stuff by the end of the chapter, but especially to lead off, we would want to lead off with this with little understanding of probability. But one of the things that chapter 5 looks at, which can be very, very helpful if you don't understand the theoretic probability of a model, is a simulation. It's just like, I'll give you an example of a pretty complex problem that I just stumbled upon recently. I don't know if anybody does Pollyanna or gift exchanges, but we do it with the adults in my family. So it's I have a brother and a sister, my mom, and then my sister's husband and my wife. So there's 6 of us total. And what we do is we put everybody's name in a bowl, and you reach into the bowl and grab a name. So we attempted to do this a couple weeks ago, and the first 3 times in a row that people reached in to get a name, they got their own name, and we had to reset and do it over again. So it led me to be thinking, what's the probability of that? What are the chances? And it changes depending on how many people you have in that. So these are the things that interest me, that I like to think about. But one way you could do that is just by simulation. You could just put names in there and keep, like the first person to go, you say it's so-and-so, and then just keep doing it. And, do it 50 times or 100 times. And you'd be surprised you get a pretty accurate estimate of what that probability is, even though it's a really complicated problem. So what we're going to do is we're going to lean on the calculator to do this, okay? So we are going to pretend we just have people coming into the room, okay? I'll show you what I mean. So people are just going to start entering our room, and we're going to write down their birthdays. And the way that I can do this, I think I've shown you all the random integer generator on the calculator before. So I'm going to hit math, and then I'm going to go over to probability, and I want to find random integer. And I'm pretty sure the keystrokes are pretty similar whether you have the NSPIRE or the 8384. When the instructions get a little bit more specific, I have them later on in the activity. So the lowest number that we can generate is 1, and the highest we'll generate is 365. Okay, and we just want to keep on doing this. Let's start with like 50 numbers. Let's see if we can do that. I really could just do it one number at a time. I think that's the spirit of the exercise here. So let me delete the 50, and I'll just have people enter the room one at a time so we can really get a good representation of whether somebody's birthday matches. And then the idea over here is just to record the numbers, and then hopefully we'll spot a match. So what I encourage people to do here is like any numbers that crop up between like 1 to 100, throw them in here. Any numbers that are like 101 to 200, let's throw them in here. And then any numbers over 200, we'll just, and anything into the 300s, we'll just throw them in there. It might help us be able to spot a match. You'll see what I mean in a minute. You could get, and I've found that sometimes people give me a really high number, and I'm like, you sure you didn't have a match? Let me go back and find a match. So let's just have some birthdays enter the room right away. So I had 299, 217, 185. Let's go back to the whiteboard. 299, what are my numbers here? 217, 185. 278, 221. I guess 185 should be in here, right? Don't want to follow my own directions. Uh, 278, 221. A lot of numbers in the 200. All right, so far, what do we have? We have 1, 2, 3, 4, 5. 5 people in the room and no matches. All right, so we'll keep going here. Just making sure I didn't lose count there. And I get 231, 122, and 189. So it looks like we're up to 9 people in the room, still no matches. Keep going here. Do 4 more. Still no matches. I'm up to like 13 people in my room now. Let's do 4 more. Oh, we got really close there, back to back. 2 people walking in together. Okay, so it looks like, and I missed this, I actually re-recorded. We have our match here at 299. You can see I went much further along here and recorded more, but we have our match at 299, and that was with just 17 people in the room. So maybe that's surprising to you, maybe it's not, but we had 17 people in the room, and you could do if we were in the classroom, we could do the simulation and compare our notes. Usually people are somewhat surprised at that, so by the time we had 17 people in the room, 2 people had that same birthday at number 299. So next I would ask you, would you want to change your estimate? That's entirely up to you, okay? So now we're going to try a different way of simulating it. That's simulation number 3. Let's see if we can find number 2. Okay. All right. So now this one is not as simple as the first one. There's some moving pieces to it. But what I'm going to do is look at rooms of 20 people at a time. And what I'm going to do then is look at 10 of them. I think it's 10. So I'm going to basically have the calculator really quickly give me 20 numbers at a time, and then I'll sort them. So now what I'm able to do is look at, let's say we walk down the hallway in F Hall and just found, well, right now we can't even find classrooms with 20 people. We can't have more than 12. But if we could find different groups of 20 people and look at that group of 20 people and see, do 2 people here have the same birthday? And then we do that many, many times. This is really our understanding of probability. Probability is what happens in the long run. If we do something many, many times, that's what we mean by probability, okay? So I'll show you how this sorts out. If you want to try this on your TI Nspire, the directions are here in the document, and I've posted this in our Schoology page right next to the video. So I'm going to go to my calculator. This time I'm going to go to Stat and Edit. I'm going to make use of my Lists feature in my calculator. Let's clear out anything that's in there. List. And what I'm going to do is tell the calculator. I want to get back to L1 actually. So I'm going to tell the calculator to make L1 equal a bunch of random numbers. So I'm going to go math, probability again, random integer, and we're going to say give us people's birthdays 1 through 365, but give us 20 at a time. And those are the directions that I give you in the document there. So now when I press enter and I execute that, I'm going to get a list of 20 birthdays. And I'm just going to observe how many times did I get a match. So I'm going to quit out of here. Now to make this a little bit easier, I'll show you if we hit second stat, so second button in list, and we go to our options, we can tell the calculator to sort that list for us. It's going to make it a lot easier. So I'm just going to say sort list 1, press enter. So now when I go through stat and edit, I'll really easily be able to see if there's a match. See how they're listed in order from smallest to greatest? So we go through, and if there are two numbers in a row that are the same number, then I know I had a matching birthday. So I scroll through, I get to number 20. Almost thought I had a match there, no match. All right, so my first group of 20, I would come back to my document here. In my first group of 20, what did I find? This is trial 1, repeat this for 10 trials, okay? So trial 1, no match, right? I'll just put, if I get a match, I'll put Y, and if I don't get a match, I'll put an N, okay? So our very first trial found us no match, okay? So what I'm going to do now, and I'll probably pause the video so I can do it a bunch of times, but I can go over to L2 if we want to see them all right next to each other. Press enter, and I'm going to do stat. Oops, I'm not going to do stat there. Stat and edit. And I want to go up so that L2 is highlighted and press enter. So it says L2 equals. I'm going to go to math, go over to probability, and I want to do the random integer deal again. Kind of keep typing that back in. Enter it. And now we just do the same thing again. I'm going to hit the second enter. It'll be a little bit quicker that way, and just tell it sort L2 for me, please. And then what happens now, we go back to stat and edit. And our L2 is nice and sorted, and we can scroll through and see this is our second group of 20 students that we brought together, and we can check and see if we had a matching birthday or not. 294. So in our second trial, that's trial 2, we did have a match. So I'm going to do this 10 times, okay? Seems like a lot, but it goes pretty quickly. And boom, just like that. Look at how quickly I did that. And you'd be stupefied and amazed at how quickly I could do that. So I only have 6 lists here, so we would have to add some more lists along there. But let's see. In my L3, you can see I have a match there. 2 people with the same birthday, so that's going to be a yes. Then I go to L4. I have to scroll down there to see if there's any matches. L5, I see a match right away, so we know that'll be a yes. So L4 is a no. L5 we said was a yes. And let's just do L6 just to get one more trial in there. 128, we got a match. Right? So it doesn't matter if I have more than one match. We just want to know if 2 people. So here's 6 trials, right? The goal here was to do 10. I did 6, and I got, so with 20 people in the room, I would estimate 4 out of 6 times, or 2/3 times. Now remember, with probability, the more I do this, if I did it 10 times, I'll get a better estimate. But with 10 trials, we have a pretty good estimate there, okay? Okay, so I feel like it's going to be important to talk about what the actual solution to this is. So I'm going to have to flash forward a little bit and give you a little bit of understanding into some basic probability rules. So the one is a probability rule of complementary events. So if 2 events are complementary, like if one happens and the probability the other happens is 1 minus that, right? So if the probability that 2 people's birthdays don't match would be 1 out of 365, right? There's or that would be the probability of a match. So the probability they don't match would be 364 out of 365. That's just with 2 people in the room, okay? The second probability rule that I want to look at here is the multiplication rule. So if you think about for example, something real simple, toss a coin, right? The probability of heads is 1/2. But if I toss a coin twice, what's the probability of getting heads twice? Well, now these are 4 outcomes, right? And the probability of getting heads twice is only 1/4. So it went from 1/2 to 1/4. The reason for that is the multiplication rule. It's 1/2 of getting heads in the first throw, 1/2 of getting heads in the second throw, and that's 1/4. So these are the 2 rules that I'm going to make use of. I'm going to be multiplying probabilities. And also the birthday situation, much like the Pollyanna situation, is not independent. So as soon as more people keep coming in the room, the probabilities are going to change. So I'm going to try my best to walk you through what that looks like. So we start with 2 people, really simple. With 2 people, we need the new person's birthday to not match the person already there. So that's not too hard, right? Now we're going to bring another person. So the probability of a match would be 1 minus that. That's where I'm using the complementary event situation. Okay. So let's think about what happens as we bring another person into this room. And I'll try to fit in here. I might even just go ahead and type, if I can type in here. It won't let me edit the document. But so number of students, if we only have one student, the probability of no match is guaranteed. The probability of a match is 0. So we can see how they add up to 1. When we bring 2 students in, and we just talked about that a second ago, 2 students are in the room, the probability of no match is really, really likely, unless they were twins and they were in the same class. And then the probability that we have a match is 1 minus 364 out of 365. Okay. So, oops, I think I did that backwards. I'm sorry about that. We read it right. The probability of a match is really, really low. Like these numbers you're going to see are going to be very, very small. They'll start off, so we have 1 minus 364 divided by 365. That's going to be 0.0027. Okay, really, really unlikely, all right? But now what happens when 3 people come in the room? Well, this third person, they can't have the same birthday as the first person that was there, and they can't have the same birthday as the second person that was there, given that they didn't have the same birthday as the first. See what we're doing there? We're multiplying those probabilities. It's an AND statement, and that's, like I said, I'm fast forwarding a little bit. This is a probability rule that we will make use of, but you can just trust me for now, but I showed you the example with the heads. So then what happens over here, real simple, we're just going to subtract 1 minus 364 over 365 times 363 over 365. So again, as you can see, I work really, really fast. What starts to happen here is there's a pattern. I can zoom in more closely and show it to you, and it involves what we call in math a permutation. We'll study those a little bit this year, but not a ton. If you take a class in discrete math, or even like some SAT prep classes might talk about this. But notice I'm doing the same thing all the time, 364 times 363 times 362. That's a permutation, we call that, of 364 numbers, and I'm permuting 3 at a time there. And that was when n was 4. Notice in the next situation here, so when we have 5 people in the room, we're permuting 4 numbers. And then we have 365 to the 4th power, which is always 1. So I have one number that's always 1 less than the number of people in the room. It creates a formula, okay, which I'm going to eventually get back to, and we'll use the calculator for that. So let's come over here and see what's happening here. I'm taking these numbers here. These are the probabilities of no match, and you can see they start off really, really high. But by the time I get 10 people in the room, I actually now have a better than 10% chance of a match, right? 1 minus that puts us at 11.7% chance, and that a lot of people would not think that way. Like with just 10 people in the room, I mean that's smaller than some of the classes that meet at school. That we'd have an 11.7% chance of 2 birthdays matching, because in statistical terms, in terms of statistical significance, we don't call that significant. If something happens 11.7% of the time, if something happens more than 10% of the time, we don't consider that to be significant. It's not unusual. Most people would. It's like 10 people got together in a room and 2 people had the same birthdays. People would think that was, quite a coincidence. Okay, so let's jump to the calculator then and see if I can use my calculator to get to the bottom of this. Okay, without boring you with the details of creating a sequence on your calculator, I've done it. And what I did was I filled list 1 with the numbers through 1 through 50. Nothing fancy there. So let's take a look at my formula for what was happening for those probabilities, right? What was populating L2 was a permutation divided by 365 to a particular power. So the permutation was always 364. I hit my math key, and permutations are here, permuting. I was always permuting 1 less than whatever was in L1. So this is I'm going to permute whatever number is in L1 minus 1. Okay. So hopefully that doesn't mess me up with the number 1 being in there, but I guess we'll find out in a second. And then I was going to take that number and divide it by 365 raised to the L1 minus 1 as well. So this might backfire on me with the number 1 in there, but I'll just go ahead and delete it if possible. I'm not quite sure how that's going to work out for us. So hopefully this will fill my list with all of those initial probabilities. Yeah, I knew that was going to be a problem. Okay, so I used some parentheses to clean that up, and I think this might be more agreeable to my calculator. I think I had it in the wrong place too. I needed to be up here, L2 equals, and that should work. Well, I couldn't get my calculator to cooperate, and just to save us the brute force approach here to continue to do this, what you'll find is by the time you get to 23 people in a room, this value here ends up being less than 50%, and this is greater than 50%, which sort of matches what we found out within both of our simulations. The first simulation, it only took us 17 people in the room and we had a match. And then when we kept simulating rooms of 20, we actually had more than 50% of the time with a match. But the actual theoretical number, that it's greater than 50. So anytime you have a group of 23 people, you actually have better than 50% chance. So it's a good bet to make, to say, I'll bet you 2 people in this room have the same birthday. In fact, I've done that in groups of 20-some people, and always surprises people that, I'll tell them, I'll bet you somebody in this room has the same birthday. And then they start counting them off, and sure enough, somebody does. So always fun. So I hope you enjoy this exploration here, just to see some of the ways that our minds or our intuition can deceive ourselves. That a number like that, 23, seems really unusually small. Number of people have in a room, so that 2 people have the same birthday when there's 365 to choose from. But oftentimes you'll find with probability that our instincts can work against us in that way.